Integrated graphics. These processors are built directly into the same physical chip as the main computer brain, sharing both space and memory resources. Historically, early personal computers required separate, bulky cards just to display basic text and colors on a screen. By moving this graphical power directly onto the main processor, manufacturers were able to drastically reduce the size, cost, and power consumption of everyday laptops and office computers. While they're not designed to handle heavy, three-dimensional rendering or intensive modern gaming, they provide more than enough power to flawlessly stream high-definition video, browse the web, and run standard desktop applications. Their incredible energy efficiency is the primary reason modern ultra-thin laptops can easily last an entire day on a single battery charge. Dedicated gaming graphics cards. These are large, independent pieces of hardware completely separate from the central processor, featuring their own dedicated memory and extensive cooling systems. They evolved during the late 1990s as video games transitioned from simple two-dimensional sprites to complex, fully realized digital worlds that required massive amounts of mathematical calculation. By housing thousands of specialized, tiny processing cores, they are engineered to draw millions of complex polygons and calculate realistic lighting in a fraction of a second. Gamers and computer builders highly prize them for their ability to push high frame rates and stunning visual fidelity on modern high-resolution displays. Installing one of these bulky, power-hungry components transforms a standard desktop computer into a high-end entertainment powerhouse. Workstation graphics cards. These specialized processors might look physically similar to standard gaming hardware, but they are engineered for absolute precision and flawless stability rather than raw frame rates. Professionals in fields like architecture, engineering, and feature film animation rely on them to render incredibly complex digital models without a single pixel out of place. Unlike consumer cards that prioritize speed to make a game feel smooth, these are paired with highly optimized software drivers designed to prevent crashes during days-long rendering sessions. They often feature massive amounts of specialized memory with built-in error correction, ensuring that a multi-million-dollar architectural simulation does not fail due to a random hardware glitch. They represent the silent, reliable force behind the creation of everything from modern skyscrapers to blockbuster visual effects. Data center accelerators. This bleeding-edge category represents the absolute pinnacle of parallel processing technology, permanently stripped of any ability to connect to a traditional monitor. Instead of rendering graphics for a screen, they are deployed in massive server farms to chew through unimaginably large data sets and train complex neural networks. Their architecture is heavily optimized to perform millions of simultaneous calculations, making them the driving force behind modern language models, deep learning research, and advanced scientific simulations. These massive, incredibly expensive chips consume staggering amounts of electricity and require sophisticated liquid cooling systems to function continuously. If you found this breakdown of computing hardware helpful, please subscribe